All right, welcome everyone back to the advanced technology track. Platform as a service is something that I've been very interested in for quite some time, and I think it's become clear that you need a high degree of automation in order to make all these massive number of containers work. And so I'm excited to introduce Diptanu Choudhary from Netflix to talk about Titan, a platform as a service-like environment that they've built.
Cool, thanks.
Take it away.
I assume everyone can hear me? Thanks to the organizers of DockerCon for having me here. This talk is about the work that we are doing at Netflix with Docker to build a highly available platform for shipping and running thousands of containers that enable us to run distributed systems on the cloud. We have been using Docker since the pre-1.0 days. And today, I'm really excited to be here and to talk to you about our experience, our journey so far, and what we have learned, the architecture of our system that we have built, and where we are going with Titan in the near future. So in a nutshell, let's jump into what Titan is. In a nutshell, Titan provisions and supervises clusters of compute resources via an API which is accessible to developers. So whenever an developer wants to run an application on the cloud, they basically use Titan's API to provision clusters of compute nodes on top of which their application runs inside containers. At scale, we can't treat cloud as a collection of compute nodes or a collection of co-located servers. At Netflix, a unit of deployment is a cluster comprising of thousands of compute nodes. We debug issues, do failover, et cetera, at the cluster level, not at an individual server level, because at scale, clusters make much more sense, right? So as you can imagine, the taming the complexity of a resource management and cloud operations deployment, et cetera, it's an ongoing challenge. Titan was built to make things better on all of these aspects. Applications on Titan run inside Docker containers. Titan handles cluster supervision, deployments of containers, health checks of containers, failovers, and supports multi-geography from the get-go. What it means is that using Titan, developers can treat the cloud as a collection of compute resources which are spread across the globe, and clusters of their application can span across multiple geographies. Titan offers an API which we can obviously use to move containers from one geography to another. That's very important for us. I'll come to that later. We try to offer everything that a developer needs, for example, logging, volume management, metrics, et cetera, via an API. So the design principle is that if you're running an application on the cloud on a cluster, you shouldn't ever need to SSH into any of the compute nodes or to see anything by knowing the IP address of where something is running. If you want to know logging, if you want to see how an application is behaving by seeing the logs, it should be location transparent, right? If you want to see how the performance of your application is, you shouldn't be going and running mpstat or something on a node where 10 other containers are running. So on Titan, we offer all those things as an API, which developers use to understand and run their services at scale. A little bit about Netflix before I dive into the details of Titan and the architecture, and I want to talk about why we built Titan and how does it fit into the context of Netflix. So Netflix is a video streaming company, and we have awesome originals and things like that. My personal favorite is Marco Polo. I love it. And we have over 60 million users spread across 50 plus countries, and we run a very tight ship to provide a good experience to our users in terms of availability and the service that we provide. The service Netflix.com is powered by hundreds of microservices, and I'm not exaggerating when I say hundreds of microservices. Each microservices are operated by engineers like me. We don't have a dedicated ops team. people who write software are managing their clusters at scale. What it means is that everyone, every engineer in the company is in pager duty, and hence you can imagine that we architect for our applications to be fault tolerant and architect in a way that allows us to sleep through the night when there may be a surge in traffic in some geography because because of the popularity of our service and things like that. Not only that, like we architect our systems in such a way where we can inflict pain on ourselves, right? Where we can inflict pain in such a manner where we can take down clusters, we can take down a whole region, and still the service remains alive. And this is how a service, our graph looks like of our microservice. And I was not exaggerating when I said that we run hundreds of microservices, right? This is the graph of like a frontier service which is talking to hundreds of mid-tier services and data tier services. We run our services in an active-active manner and on multiple geographies. That means that we can handle disruptions at any given AWS region. When I say disruption at AWS, I just don't mean like disruptions at the infrastructure as a service layer, but faults at our own software, faults at our data tier and things like that. So we can move all our clusters that power our user-facing services from one region to another, and we can save the day. And as you can imagine, managing hundreds of microservices on tens and thousands of servers on 3 different regions is not an easy affair. The continuous delivery and build tools at Netflix are pretty awesome, right? Like we can ship code really fast and get things into production really fast using our tools, our continuous delivery tools. But we wanted to make things even better, right? So the bar was really high for us when we started, and we wanted to take the bar even higher. What we wanted is we wanted to make a vertically integrated service which would allow us to not only supervise clusters, but manage resources and provide APIs to developers where they can consume and manage resources really easily. So what we were really looking for is like a PAAS, right? But not really a PAAS in the traditional manner. We wanted all the operational benefits that PAAS provides, right? Like PAAS provides a suitable API for looking at logs, looking at metrics, scaling up clusters, scaling down clusters. And when I say scaling down clusters, I'm not saying scaling down servers. I'm saying scaling down applications, because as a developer, they care about the applications that they run, and everything else that runs on the server is pretty much helps the process that are running. So we wanted the application developers now to be thinking in terms of their applications and not worry so much about where they're running, in how many geographies they're running, and how to provision their applications, how to supervise them, etc. Right? But at the same time, when we wanted a PAAS, we didn't want the PAAS to be opinionated. We didn't want a PAAS for running Node.js application or a PAAS for running Java applications. And that's where containers come in. With containers, we say that, hey, you know what, as an application developer, you can package your application in a lightweight container where all the bits that support only your application is in that container, and then we will supervise your containers and we will run your containers and all that. Right? So packaging was something that we really wanted the developers to control. We didn't want to come in the middle of what developers wanted to run and what the design and architecture was. And then at the same time, we were seeing an interesting phenomenon that was happening in Netflix over the last 1 year. We saw that people were writing their own resource schedulers for their workflow systems. There were workflow systems which were basically triggered by events. There were workflow systems which were triggered by data. For example, once in an hour, maybe some feed is arriving, and then whenever the feed arrives, the need of the business was that we needed to run some applications which would consume the feed, and that's it, right? And then do some data crunching on the feed, and then write it somewhere, and then go away, right? So people were writing their resource schedulers to be supporting those kind of use cases. And so what we wanted to do is we wanted to provide the lowest common denominator. What we wanted to do is provide them a scheduling system, provide them an infrastructure where they can run processes, where they can trigger processes via an API call and build their workflow systems on top of it. By doing that, what we are allowing developers to get is the things that we have built onto Titan, fault tolerance, auto-scaling, and things like that, they get those out of the box for free, while concentrating on their domain-specific systems. So we take operations like very seriously, I talked about running things in an active manner. What it means is that we have a lot of tooling around that, and right now what happens is that the movement of traffic, the movement of clusters from one region to another happens by scaling up and scaling down clusters in the regions that we are working on. And we wanted SREs and developers like us who are moving things around to have a consistent API which works for all different application stacks and all different use cases, and have a consistent user experience around those APIs. So Titan has an API where we say that you are running a cluster in this geographies, and now I want to change that dynamically, and I can say that run lesser in this particular geography and increase the number of containers that you run in another geography. And a quick note about geography: whenever I say geography, it basically means an Amazon region. If you are running in a traditional data center, you can think about regions as different sites for your data center. So that's the correlation that I think you can make with when I say region, with the use cases that you might have. One of the things I often ask users is why they are using Titan. Speed of innovation is a very key aspect at Netflix. We design our tools and our systems so that we can innovate and move faster. And very often, users of Titan comes and tells me that, hey, you know what, we love using Titan because we can move to production really fast, right? When they are baking containers, they are not baking a whole server. They are just baking the bits of their application on top of a base container. And again, our build infrastructure does a good job here, where we have something called bakery internally. With bakery, you can build containers where you have a Docker file or something in a repository, which will bake your application on top of a base container. And then when the container is baked, then we can basically start those containers or launch a cluster of those containers in a matter of seconds in any of our environments or any of our regions. So that was really cool. And that sort of helped getting Titan become popular within Netflix. And again, we run our own private registries. So that means that our bakery knows where our private registries are, and we can optimize how close the containers can be so that we can start those containers really fast whenever developers want them. And Amazon has a concept of auto-scaling groups. We use auto-scaling groups everywhere in Netflix. We use auto-scaling groups as a control plane for running our web services. And auto-scaling groups are awesome, but they're awesome for long-running services. For web services, the use case where I was saying that you might have evented systems where you are starting off a process because an event has arrived, there is a impedance mismatch there, because auto-scaling groups target servers, whereas when you are provisioning processes and triggering of processes, it's much more nicer to be closer to the process. Since with Titan, we are basically doing process supervision using containers, the lifecycle of a container is tied to the lifecycle of process. And when we are supervising containers, it's easy for us to spin up containers very fast in an existing EC2 instance. So that was another key thing. And then we obviously wanted to increase the application density of the applications that we run on Amazon. So what it means is that if we are running applications like a Node.js service or something which is event loop based and takes a single CPU, I don't need to be running on a server which has one CPU. I can still run a Node.js application on an I don't know, an R38XL instance which has SRIOV and a 10 gig Ethernet pipe, which has a good networking story around it, but I can still run many of those Node.js applications on a machine which I want. So increasing application density on Titan doesn't mean that I need to go back on a instance that I don't like. Developers can still be on a machine where they get SSDs or higher network pipes and things like that, and still get to achieve higher application density. Now, how does Docker fit into the picture? So Docker, we chose Docker when we wrote Titan because we wanted like process isolation from the get-go. We wanted, we wanted immutability of artifacts because we wanted. It's really nice when you know that in a cluster, everything, all the bits of the application that you are running is homogeneous, and that homogeneity comes from having golden images, right? So today, like we bake armies, so we know that all the things that are running in our army are same, and so it gives us a greater degree of confidence about the software that we are running. With Docker, like we could preserve it because now I still have the concept of immutable containers, and in that immutable container, I know that all the bits are same across. There is no like dilemma whether we are going to be converging when an application is starting up. If you're running a traditional configuration management system. Not saying that traditional configuration management systems are not useful. They are still useful in cases where you want to make sure that the base containers and things are all similar and stuff like that. And going back to the original point about lightweight virtualization, 1 year back, a little more than 1 year back now, when we started the project, Docker, as I said, was still in the pre-1.0 days. There were many things that we could consider. Like we had, LXCs. LXCs has been around for quite a long time. They are on the user space. The reason why we didn't use LXCs was that LXC directly was that we were starting to write our own wrappers on top of LXCs to make it more usable. And Docker filled that gap. Docker was sort of targeted towards making C group and namespaces more accessible. So we didn't invest in writing our own wrapper on top of LXC and C group and namespaces. We instead chose to use Docker because Docker gave us that. That tooling around managing C groups and namespaces on the kernel. Then there were other aspects around tooling and distribution. One of the good things about using Docker was that we didn't have to go to the users who are using Titan. We didn't need to train them how to make containers. There are so many resources around the web where people could find resources around how to build containers and things like that. And those were really important like 1 year back. Because we, at the same time, like, with our limited resources, we could reinvent all aspects of containerization, all aspects of distribution, all aspects of tooling of how to make containers. So the tooling bit was really important, and it filled some gap there. So today on Titan, we are shipping thousands of containers across all different Amazon regions where we are present. We are present in 3 regions, and we are shipping thousands of containers in each region. And Docker is the only way to run applications on Titan. That's a decision that we made from the very beginning. This is how the Titan API looks like. I'm sorry that it's a little, it's too crowded up there. But as you can imagine, like in Titan, like this is a specification of a job. In a job, like you basically say what is the image that you want to run, the number of tasks that you want to be running, the memory for each task, which is basically like a container, the locations where you want to be running. In our case, it's basically like we don't run on a traditional data centers. In our case, it's basically like Amazon regions where we are running. And then you basically can say how many times you want us to be restarting the tasks if they fail, how many times, for how long you want the tasks to be running, how many IP addresses you need, and things like that. So that's pretty much it. And we also support volumes. I'll come to that later. So a container can be like 4 MB, but it can have a volume which can be like 200 GB, for example. And we can basically, we can optimize the volume based on the file system we need. We don't have to rely on the root FS of the container to be like really efficient for writes and reads. There is a good story around here. I'm going to come later. And this is like how a compute node on Titan looks. We use Mesos, more on Mesos later. And then we have our own logging agent and monitoring agent. We have our own volume manager. We have our own network interface manager. And we use ZFS on Linux for our volumes. More on ZFS on Linux later. And then we run on Amazon EC2, which is basically like a Zen-based runtime. And we are using Ubuntu, a vanilla Ubuntu distro right now, and we have basically, we are on like a newer kernel, which basically supports a lot of newer things that the kernel has for making C groups and namespaces efficient. More on logging and monitoring later. And from a 1,000-feet level, this is how Titan looks like. Titan is not a monolithic system. What it means is that we are not trying to develop everything that the end users needs on Titan, right? We use Mesos for discovery of resources on Amazon. We use Mesos for launching a process. And then the actual processes are basically like Docker containers. We have our own Mesos scheduler. We do very complicated, not very complicated yet, but we do like some kind of scheduling where we basically understand the cluster state, and we can schedule based on the constraint. So if you want to be spreading your containers across zones, across regions, and things like that, we can do that. We can make sure that a process which is CPU intensive is not running with another CPU intensive process, or too many network-heavy containers are not running on the same machine, right? So we do all those kind of scheduling in our own scheduler, in our own Mesos scheduler. And then we have a Titan API, which basically provides the public API to the distributed systems that people are running on top of Titan, right? So we have Spinnaker, which is our cloud deployment system, which basically talks to Titan via the Titan API. We have Meson and Dagoba, which are workflow systems, which are very domain-specific. Meson is like a typical workflow system where a stage triggers another stage in the workflow. Dagoba is a data-driven workflow system. And we have our own autoscalers and things like that. From a 5,000-feet level, this is how Titan looks like. We always sync job specification from one region to another. So when we have to move containers from one region to another, because of some faults and stuff in that region, we still have the cluster specification available. Titan manages disks for containers. Like we manage ephemeral volumes, and we mount those ephemeral volumes on containers. So your container can be really small, and you can have like a bigger volume. We use ZFS on Linux on Titan. It architecturally enables us to do things like snapshots, moving snapshots around the cluster and things like that. So this will help us in the future when we are running more persistent type of containers on our fleet. Logging has been an ongoing. Logging has been like an ongoing area of us reinventing on Titan. We really started logging by saying that all your logs are going to be on the host on which it's running, and we are going to be retaining them as long as the container lives, but that doesn't really work since containers can go away, and people want them to be debugging. So we provide logging via an API in a location-transparent manner. So even if the container moves around between hosts because they have been restarted, you can still be getting the logs of the container via an API, and we back them up in S3. In terms of networking, the answer there is different. Our use case was that we are going to be running really network-heavy applications on Titan, applications which are doing a lot of I/O on the network. On EC2 Classic, we use Mesos as a broker for port allocation, because in EC2 Classic we have a single network interface, and if you're running multiple containers, there is no other way of doing it other than running an SDN overlay network on top of it. But we chose to basically use, broke the ports via Mesos, and then we say that you're not going to be getting a single network interface. You're going to be getting a port on the network interface. It's not really nice, but that was what we could do on Amazon EC2. In VPC, there are much more options. In VPC, what we do is every container get its own IP address, and what we do is we are taking advantage of the new network plugin that Docker has. I don't think they have landed it on a release yet. It's still on master. I think the code is merged into master now. So what we have is we are using that to create a remote network plugin, which will basically allow us to take in charge of setting up the networking for the container. So Docker doesn't set up networking on its own anymore. It basically hands up hands over the responsibility, and then we create a network interface. We move the network interface in the namespace of the container. So you still have a networking stack which is isolated on a per container basis, but you still have all the containers being routable across your network in a VPC. We don't use Mesos anymore for networking and for port management in VPC. So our networking plugin is still like in a beta state. We don't really run any production grade workload using the network plugin. Part of the reason is there is no official release of Docker which does it yet, but it works, and we are continuously improving it, and we're going to be rolling it out soon in production when we have more confidence on it. In terms of monitoring, we publish hundreds of C group metrics into our internal monitoring system. We use the C group notification API for alerting users when a container dies because an out of memory exception happened. Users can see metrics at a per container level. So you don't really need to be like, if you're running on Titan, like you don't need to be guessing like what is the number of times I have been throttled out of the CPU because a tenant on the same host was trying to get more CPU. So you'll get all that metrics on a per container basis. And even when the container moves around, like you'll still get like a chart, which is basically like a continuation. And you can do like things like dicing of the performance of the containers of the same applications running on different EC2 machines. And it allows us to do interesting things when we are triaging performance issues, because of a busy neighbor, we can see that a container is not doing so well. In the future, we will feed all that metrics back to our scheduler, and our scheduler can take intelligent dynamic scheduling decisions based on the C group metrics that the kernel is publishing. Coming back to failover, we offer an API where like clusters can be drained, and this is not only useful for when fault happens, but nobody really speaks about what do they do to run systems like Titan in production. What happens when you are deploying like a newer version of kernel or patching the kernel, right? And we see this all the time. We patch the kernel and we create a new foundation server. What happens to the containers then, right? So we have the flexibility of draining a cluster from all the containers from an old cluster to a new cluster, and without the users even knowing, right? There can be faults which can happen at a node level, like there can be like disk which might go wrong, or the Docker daemon might misbehave, like 1 out of 1,000 nodes can be misbehaving. So does it mean that I wake up in the middle of the night? No, we don't really need to wake up in the middle of the night. What we do is we keep a scoreboard of how well a node is doing on the fleet, and if that node is seeing a lot of crashes for downloading containers, starting containers, we take that out of the fleet. And then since we are using auto-scaling group under the hood, we can basically, the auto-scaling group is replacing that node for us, and we eventually get a healthy host. Again, like, it allows us to sleep through the night and not do anything drastically different because there is a fault in like one node or one zone or something like that. Auto-scaling is pretty important to us. We do two levels of auto-scaling. We can scale the underlying compute nodes on top of which containers run. So the more the number of users are running on Titan, we scale out. We don't run with like a large enough fleet so that we are wasting resources. We always try to utilize the most amount of resources that we are getting from Amazon. Auto-scaling rules can be applied based on performance metrics of applications. So as a user, you can define some thresholds in terms of the C group metrics that we report, and then our autoscalers can scale up the clusters of containers. This is a graph that I took this morning. So this is like one of our clusters. We run many such clusters. So as you can see, some event might have happened which might have triggered more containers at around before noon. And you can see that cluster growing to 140, and then slowly it came down to like, I don't know, like around 36 under 40. And so when people are throwing more workload on Titan, like we don't need to be like provisioning more or be cognizant of the fact that, you know what, like we might be wasting resources if we are always running with like thousands of nodes. And then we have two types of autoscaling. We have like predictive autoscaling and reactive autoscaling. We have a predictive autoscaler at Titan called Scryer. What Scryer provides us is some way of saying that if you are running 100 containers yesterday around this time, so you might be running 100 today as well. So with predictive autoscaling, we can do like linear regression models and pre-scale our clusters of container and make sure that we are always in a place to be serving traffic from those applications or be doing batch processing stuff. Reactive autoscaling happens based on thresholds, predefined static thresholds. And lastly, like I wanted to talk about like where we are with Titan, and it's not something that we have been doing since last month. It started off from a conversation that we had between a couple of us, and we wanted to see like if we can have a fault-tolerant, highly available system for running cron jobs, right? And Titan started from there, and people liked it, and we started running non-mission critical applications on it, and people liked it even more. And today we are running mission critical batch jobs in production. And it basically grew up from there. Like we didn't like start one day with a grand vision of like writing Titan. And today we are doing prototypes of running web services from Titan. Like the work that we are doing around custom network plugin is around that to help us serve web services. In the near term, we are going to be running parts of our data pipeline on Titan, like the messaging system which powers Netflix, parts of it, not like entirely. And then in the future, like end of like this year or sometime next year, we are going to be trying to be running the Netflix API, which is like the front door of Netflix, which serves over 2 billion API requests every day, even more now, on Titan. And towards the end of this year, we will be working towards open sourcing Titan. And if you want to work with us on Titan, collaborate with us, it would be a good time now to chat with us, and we can collaborate with you and see if it meets your use cases. So thank you for coming to this talk. And there are a couple of Netflixers around. So come and talk to us if you're interested in this, or if you're interested in Simian Army stickers. We are here, so find us and talk to us. Thank you.
Great, thank you. So you answered my question about how long you've been working on this. How big has the team been? Is it just those same couple of guys that were trying to fix cron?
So the team has been mostly like 1 or 2 developers. Yeah, I would say 1.5, 2-ish.
Nice. What questions do you have for the 1.5 developer behind Titan?
It's going to be open source like later in a couple of months. We are moving at a really fast pace. We are changing the public APIs so much because we are still experimenting with Titan. Like today we run like Titan in production, but we are still moving really fast. So let the public API settle down a little bit. Let the network plugin settle down when Docker makes a release with the plugin stuff, and then we will open source it.
So with your scheduler, how much do you have to deal with sidecar containers or like symbiotic containers?
Oh, OK. So today, like we have the concept of running certain things on the host. So what it means is that whenever a host comes up, like we know that there are a couple of system-level services which are going to be running. So we make sure that those are running, and you can also say that a task can be running with another task all the time. So tasks can be co-located. So you can have a web service app which is running in a container, and you can have like a log shipper app running in another container on the same host. So via the Titan API, you can say that, hey, you know what? I want all these tasks to be co-located either in a single machine or in a zone or in a region.
Go ahead.
How long have you been using Mesos as part of the application, and have you been using Kronos and Marathon as well?
Yeah, so we have been, that's an interesting question. So we have been using Mesos from the get-go on Titan. We have been, so when we started writing this stuff, there was no Marathon. Marathon was still early days. And Marathon, there are a lot of things that we wanted Titan to do, which Marathon didn't take care of at that stage. Maybe they will in the future. So to meet the needs of the cross data center, cross region kind of use cases, automatic healing, and then fault tolerance and things like that, we didn't want to use Zookeeper, for example, as a store for storing the job metadata. We have our own service where we maintain the state using Swim and Raft for the job metadata and things like that. So we have been, so basically that's the thing. We are using Mesos from the very beginning.
I have a question about how you came up with your predictive autoscaler. Is that stuff that's baked in, that you developed from scratch or using other tools?
We didn't build this stuff on Titan. This is the work that has already been happening in Netflix for a really long time. You can look up the Scryer project on the Netflix tech blog, and it gives you like a good idea of like what Scryer does. It's basically like linear regression models and things like that. But yeah, we didn't develop it for Titan. We did a lot of integration with that stuff. There is one. Okay.
What do you do for your networking? How do you do virtualization in between different regions, different clusters of containers?
Yeah. So okay. So I think this is a very this is not like a straightforward question, I guess, and so the answer is also not straightforward. So I think networking is one aspect, right? Containers being routable is one aspect of it. So in VPC, as I said, like you can have containers which are routable to other containers, and in EC2 Classic they are sharing the same ports. But internally, for discovery of containers, like we didn't develop anything on Titan. We have a service discovery system in Netflix called Eureka. So containers, applications running in containers on Titan register with Eureka, and then they find each other via that.
So question over here.
So yeah, so the applications running in container, they know what is the IP address, what is their IP address on which port they're listening to. So they register with Eureka saying that, hey, I am this application running on this IP address and on this port.
Is there any specific dependency on EC2, or will this work in any configuration?
So we are running this on EC2. So we are running Titan on EC2, but doesn't mean that you can take Titan and run it in your data center. So much like our other open source software like Eureka, Ribbon, and stuff, like we run them on AWS because we are on AWS. But a lot of people have taken those and are successfully running them in other environments. What it means is that the autoscalers that we have implemented works for Amazon because we call AWS APIs. So if you're running them on your data center, you'll have to write an implementation of the interfaces which talks to your own autoscalers, be it on your data center or DigitalOcean or Google Compute.
So you mentioned that you're going to be using Titan at the end of this year for your front-end API.
Yeah.
Is there anything that you had to do special for network security or security in general?
So that's an ongoing challenge. We didn't, and that's why I said future term. Like I didn't have a date there because we are still like figuring out a lot of things about security and how would security groups work and things like that. I don't have a concrete answer for your question right now around security. If you are talking about IAM roles and things like that, we have an answer. We use the STS service, and we have our own IAM service which fronts on, which is backed by STS and things like that. But we don't really have solved all the things there. It's still an area of ongoing work.
So that was actually my question. How do you deal with instance profiles and roles? Specifically with this STS.
Yeah. So and again, this is the solution that we have. Like if you guys have better ideas, please come and talk to me. What we do is when like something like Boto or the Amazon SDK is talking to the Amazon metadata service, we basically hijack that API call and move it to our service, and our service can basically know what is the source IP. And since we are provisioning the containers ourselves, we know which container has asked for it, and then we can give you like a credential that we have got from STS, and which we know is going to expire after some amount of time. So that's the solution there. It works. It's sort of like a proof of concept. I can't claim that we are doing at a scale of tens of thousands of containers. We will get there, but that's the state right now.
And last question.
I actually have a couple of questions. So, can you speak? So, in regards to the control plane of the Titan service, so my question is in regards to what are the global services in the control plane and what are the
yeah, so we wrote like a distributed store almost, distributed job store almost, where basically, you know, like you are going, the control plane is highly available in the sense that whenever like a task update comes or a job specification comes, a user specification, specified job specification comes, we are replicating it across like multiple nodes using log replication. And then it's not so simple because if you're replicated, that means that whenever you're updating the state of a task or a container, it needs to be going into all the nodes. That means we need some leader election as well. But we don't like highly consistent systems at that scale because if you're highly consistent, that means that you won't be like partition tolerant. So we are eventually consistent at the cluster membership level, but there we do leader election on a subset of the nodes of the cluster. So a job can have, there can be one node which will be leader elected for like say hundreds of jobs. And then there will be like other nodes on the job store which will be leader for the other jobs, right? So if I have a failure there, like not everything in Titan is down. There will be an outage, but that outage will be limited to the amount of nodes I have lost.
Okay, the follow-up is, do you have any services that require global load balancing to be done across zones? Or you know, if there is a use case, how would you handle that with Titan? Because you will need a global service then, at least to do the global load balancing.
So Titan, so what happens with Titan is that, so zones is one aspect, but regions is another. So if you're talking about zones, that means that we have multiple zones in one region. What it means is that you can basically say that, hey, you know what, I want to spread the containers evenly in all the zones. So that Titan supports. You can put that as a constraint.
All right, thank you.
Thanks.